Welcome back. Last episode, we found the 4 fundamental subspaces of a matrix. Today, we count their dimensions and discover one equation that organizes the whole theory of solving linear systems: rank plus nullity equals n. The rank is the number of independent directions the matrix actually uses. The nullity is the number of directions it collapses to 0. Add them, and you always get n, the number of columns. Then, we assemble these pieces into Strang's big picture, the single diagram that shows the matrix A carrying the row space onto the column space, while the null space is crushed to a point. From that picture, 2 of the oldest questions in mathematics answer themselves. When does a system have a solution? When is that solution unique? Existence will turn out to live in the output space, and uniqueness in the input space. Let's count first, then draw. Here is the theorem, and its proof is just careful bookkeeping. For any matrix A with n columns, the rank plus the nullity equals n. To see why, reduce A to its reduced row echelon form and look at the columns. Every single column is exactly one of 2 kinds. It is a pivot column, and there are r of those where r is the rank, which is also the dimension of the column space. Or it is a free column, and each free column produces exactly one special solution in the null space, so the number of free columns is the nullity, the dimension of the null space. There is no third kind of column. So if we add the number of pivot columns to the number of free columns, we must get the total number of columns, which is n. In symbols, r plus the quantity n minus r equals n. That is the entire proof. No input direction is ever lost. Each one is either used by the matrix or sent into the null space. It helps to read the theorem as a conservation law. Picture A as a transformation from Rn to Rm. It has n input dimensions to work with, and the theorem says those n dimensions split into 2 parts. The first part, with dimension r, survives. It becomes the image, also called the column space, the set of outputs the matrix can reach. The second part, with dimension n minus r, collapses. It becomes the kernel, also called the null space. Every direction the matrix flattens to 0. The 2 always trade off. If the matrix squeezes more of the input to 0, giving a bigger null space, then it has less left over to map out, so the rank is smaller. If it preserves more directions, raising the rank, then it must kill fewer, lowering the nullity. Dimension going in equals dimension coming out plus dimension lost. Nothing appears from nowhere, and nothing vanishes unaccounted for. Now assemble the picture. We have 2 spaces. The input space, Rn, splits into the row space of dimension r, perpendicular to the null space of dimension n minus r. The output space, Rm, splits into the column space of dimension r, perpendicular to the left null space of dimension m minus r. Now watch what A does. Any input vector x can be written as a row space part plus a null space part because those 2 pieces fill all of Rn. When A acts, it sends the null space part straight to 0. That piece is crushed. What remains is the row space part, and here is the beautiful fact: A maps the row space 1-to-1 and onto the column space. Both have the same dimension, r, so restricted to the row space, A is genuinely invertible onto the column space. Strip away the null space and every matrix is, at heart, an invertible map between 2 equal dimensional spaces. That is the big picture in one sentence. Use the picture to answer the first big question: for which right-hand sides B does the system Ax equals B have a solution? Since Ax is always some combination of the columns of A, the product can only ever land inside the column space. So the system is solvable exactly when B lies in the column space and not otherwise. That is existence in one line. A special case, the system is solvable for every possible B exactly when the column space fills the whole output space Rm, which happens when the rank equals m, the number of rows. We call that full row rank. In practice, you test whether B is in the column space by row, reducing the augmented matrix and checking that you never produce a row that reads all zeros on the left but a non-zero number on the right. Equivalently, B must be perpendicular to the left null space. Now the second big question: when a solution exists, how many are there? Suppose xp is one particular solution, so A times xp equals B. Then for any vector xn in the null space, A times the sum xp plus xn equals B plus 0, which is still B. So every solution has the form xp plus something from the null space, and conversely, every such vector is a solution. The complete solution is one particular solution plus the entire null space. This makes uniqueness immediate. The solution is unique exactly when the null space contains nothing but the 0 vector, that is, when the nullity is 0, which means the rank equals n, full column rank. If the nullity is positive, there are infinitely many solutions, a whole shifted copy of the null space. Notice the clean separation. Existence is governed by the column space in the output space. Uniqueness is governed by the null space in the input space. They are 2 independent questions with 2 independent answers. This is the diagram to memorize. On the left, the input space Rn, drawn as an oval split into the row space on top, dimension r, and the null space below, dimension n minus r, meeting at a right angle at the central 0. On the right, the output space, Rm, split into the column space on top, dimension r, and a left null space below, dimension m minus r. The bold arrow labeled A sweeps from the row space across to the column space, 1 to 1 and onto, matching the two equal dimension spaces. A second arrow drops from the null space straight down to the single 0 point on the right, because A sends everything in the null space to 0. A sample input x is shown split into its row space part and its null space part at a right angle. Read the whole theory off this one image. Rank plus nullity equals n along the bottom, existence on the right in the column space, uniqueness on the left in the null space. This figure makes the complete solution visual. The blue line through the origin is the null space, the set of all vectors A sends to 0. The green line, parallel to it but not passing through the origin, is the solution set of Ax equals b. The gold arrow from the origin reaches one point on the green line. That point is a particular solution, xp. Now here is the key idea. To reach any other solution, you start at xp and slide along the blue null space line. Every point on the green line is xp plus some null space vector, and every such sum lands back on the green line. So the solution set is nothing but the null space, picked up and shifted over by one particular solution. If the null space were just the origin, the green set would shrink to a single point, and the solution would be unique. The size of the solution set is exactly the size of the null space. Let's read all four conclusions of one matrix, the same A from last episode. It reduces to a form with pivots in columns 1 and 3, so the rank is 2. The matrix has 4 columns, so n is 4, and 3 rows, so m is 3. Check rank nullity first. The rank is 2. The nullity is the 2 free columns, and 2 plus 2 equals 4, which is n. The bookkeeping balances. Now the structural conclusions. The rank, 2, is less than m, which is 3, so the matrix does not have full row rank. Its column space does not fill R3, which means some right-hand sides B cannot be solved. The rank, 2, is also less than n, which is 4, so it does not have full column rank. Its null space is non-trivial, which means that whenever the system can be solved, it has infinitely many solutions. So for this matrix, existence sometimes fails and uniqueness never holds. All of that just from the rank. Now let's actually solve a consistent system with this matrix. Take B to be the vector 4, 11, 7. Augment A with B and reduce. The system turns out to be consistent, leaving the equations x1 plus 2, x2 plus x4 equals 2, and x3 plus 2x4 equals 3. To get one particular solution, set the free variables x2 and x4 to 0. Then x1 is 2 and x3 is 3, giving the particular solution 2, 0, 3, 0. For the rest, we add the null space, whose bases we found last episode, the vectors -2, 1, 0, 0, and -1, 0, -2, 1. So the complete solution is x equals the particular solution plus c1 times the first null vector plus c2 times the second, where c1 and c2 are any real numbers. It is a two-parameter family of solutions, which is exactly what nullity 2 predicts. One particular point plus a two-dimensional null space sliding it around. For contrast, the happy case. Let A be the 2 by 2 matrix with rows 2, 1, and 1. Its determinant is 2 times 1 minus 1 times 1, which is 1, non-zero, so the matrix is invertible. The rank is 2, which equals both m and n, so it has full rank. Rank nullity gives 2 plus 0 equals 2, so the nullity is 0 and the null space is just the 0 vector. Read off the consequences. The column space is all of R2, so the system is solvable for every right-hand side B. Existence always holds. The null space is trivial, so whenever there is a solution, it is unique. Uniqueness always holds. Existence plus uniqueness for every B is precisely what it means for a matrix to be invertible. In the big picture, both null spaces vanish, the two ovals shrink to pure row and column spaces of full dimension, and A becomes a single one-to-one onto map from Rn to itself, with the solution given simply by x equals A inverse B. It is worth laying out every possibility, because there are exactly 4. The two yes or no questions are, does the rank equal m, the number of rows, giving existence for every B, and does the rank equal n, the number of columns, giving uniqueness? Cross those and you get 4 cases. If the rank equals both m and n, the matrix is square and invertible, exactly one solution for every B. If the rank equals m but is less than n, the matrix has full row rank but free variables, so there is always at least one solution and in fact infinitely many. If the rank equals n but is less than m, the matrix has full column rank, so there are no free variables and at most one solution. But some B cannot be reached at all, so you get either 0 or one solution. And if the rank is less than both, you get either 0 or infinitely many. Full row rank controls existence, full column rank controls uniqueness. The shape of a matrix already hints at how it behaves. On the left, a tall, narrow matrix with more rows than columns, n greater than n. Its rank can be at most n, which is less than m, so its column space can never fill the whole output space. That means some right-hand sides b simply cannot be reached, and the system may have no solution. The little big picture icon underneath shows a large left null space soaking up the extra output dimensions. On the right, a short, wide matrix with more columns than rows, m less than n. Its rank is at most m, which is less than n, so by rank nullity, its null space must have positive dimension. A non-zero null space means the solution, when it exists, is never unique. There are always free variables. So tall matrices risk having no solution, and wide matrices can never pin down a single one. Shape sets the default, the exact rank fills in the rest. A short history. The star of this theorem is rank, defined by James Joseph Sylvester in the 1850s as the size of the largest non-vanishing minor. Georg Frobenius, late in the 19th century, made rank an intrinsic property of a matrix and proved the rank inequalities for products. The rank-nullity theorem itself, also called the dimension theorem, was crystallized in the early 20th century in its cleanest abstract form. For any linear map, the dimension of the kernel plus the dimension of the image equals the dimension of the domain. That is exactly our statement, nullity plus rank equals n, dressed in the language of transformations. And the visual packaging, the big picture that turns this counting fact into one unforgettable diagram of two ovals and an arrow, is once again the contribution of Gilbert Strang and his MIT course. We have been drawing his picture all along. Let's recap. The rank-nullity theorem says rank plus nullity equals n, because every column is either a pivot column counted by the rank, or a free column counted by the nullity. Read as a conservation law, the n input dimensions split into the part that survives, of dimension rank, and the part that collapses to 0, of dimension nullity. The big picture draws this. A maps the row space 1 to 1 and onto the column space, while the null space is crushed to the 0 vector. From the picture, existence and uniqueness fall out. The system Ax equals b is solvable exactly when b lies in the column space, and solvable for every b exactly when the rank equals m. The solution is unique exactly when the null space is trivial, which means the rank equals n, otherwise the complete solution is one particular solution plus the whole null space. When the matrix is square with full rank, both hold for every b, and the matrix is invertible. Next episode, we keep the same vectors and the same maps, but change the bases we described them in, and watch the coordinates transform. Today we proved the rank-nullity theorem and drew the big picture. The theorem says that for any m by n matrix, rank plus nullity equals n. The rank is the number of pivot columns, the number of independent directions the matrix genuinely uses. The nullity is the number of free columns, the dimension of the null space. Since every column is either a pivot column or a free column, the two counts add up to n, the total number of columns. Then we assembled Strang's big picture of the four subspaces. The matrix A takes the input space, Rn, splits it into the row space and the null space, crushes the null space down to the 0 vector, and maps the row space 1 to 1 and onto the column space inside Rm. So A is secretly an invertible map between the row space and the column space, both of dimension rank. From this picture, solvability and uniqueness fall out. The system Ax equals b has a solution exactly when b lies in the column space. The solution is unique exactly when the null space is just the 0 vector, that is, when the nullity is 0. Existence is a question about the output space. Uniqueness is a question about the input space. Next episode, coordinates and change of basis. If you got something out of this, please like the video, drop a comment with what clicked for you or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching. See you in the next one.